Right, hello guys. So we are on to the next section of the finite element method for truss structures, or whatever I've called this module this year. And where we ended up with at the end of last lecture, we developed a piece of code that enabled us to automatically create some 4x4 matrices. Now these would be for a given element. These would be equal to whatever the stiffness, which is just a scalar of that element. And then we have cosine squared, cosine sine, minus cosine squared, minus cosine sine. And I'm not going to bother drawing the rest of it, but it's this matrix here, and we're going to end up, we're able to programmatically and automatically create those for each element. We know that when we create a global structure, so for example, in the problem that we created, when we solve this problem very manually, this problem has 3 nodes, A, B, and C. Okay, just moving the cat off the desk. A, B, and C, 3 nodes, and each of these nodes has an associated global displacement. So we have VA, UA, VB, UC, sorry, VB and UB, UC, and VC. So there are 6 global displacements, and that gave us a 6x6 stiffness matrix. So our global problem was a 6x6 matrix multiplied by a 6x1 vector. So UA, VA, UB, VB, UC, and VC, and that was then equal to the forces present upon each of those nodes. These should be uppercase: FXA, FYA, FXB, FYB, FXC, and FYC. So at the moment we can create some 4x4 matrices, and somehow these need to go into this big matrix here. Now when we did this problem sort of manually, we could see that parts of those 4x4s corresponded into different parts of this matrix here. Now what we're going to do today is we're going to look at a means of taking the row out of the column out of that connectivity table that we produced last week. So that was, let's go back here, let's have a look here. So taking this column, and we're going to work out from here how we can take the elements of that 4x4 matrix and put it into a form that we can then convert into this matrix here, because we're going to do it in 2 steps. So to make this matrix here, so we need to do 2 things. The first of which, well, let's say we need to do 2 things after we've constructed all of those 4x4s. So the first one is we need to take those 4x4s and expand them into a 2n by 2n matrix, where n is the number of nodes in the system. And if we're smart, and if we do this properly, such that we make sure that we take those 16 elements within that 4x4 and put them into 16 correct spaces in this 2n by 2n, then we can just take all of those matrices and then we add them all together. And so that second step is actually easy, add them all up. This step is actually not that difficult, but it involves quite a lot of logical programming that maybe wouldn't come naturally to all of you, so we're going to go through it today in a little bit of detail. I'm going to do this all in a Jupyter notebook, and you can do this one of 1,000 different ways, many different ways you could solve this problem. I have solved it the way that I happened to just solve it this morning. Okay, it's different to what it is in the accompanying notes. The logic's pretty much the same, but I have just chosen to solve it a slightly different way because that's the way that coding works. You choose the best way that you think of at the time, and I'm a year better at Python than I was when I first solved this. So we're going to start with this matrix, sorry, this Jupyter notebook, and I'm going to include the link to the Jupyter notebook in the description of this YouTube video. Okay, so we start here, and I include a bit of description at the top, and I include some extra work here. Now all I've included here is, let's go through and see what I've got. I import some packages that we're going to use. So we're going to import NumPy. We're importing SymPy, but only for one part here, which is just this bit that helps me to make things prettily, basically. And I've expanded how we print now. So I can now print a matrix to look really nice. So here's just a quick test of that. So these lines here are to be used. So it got things imported, and then I've defined this thing called print matrix. And so I've set my KE. This would be one of the 4x4s that I've created to be a 4x4 completely of ones. And then I'm able to print it. So this is print matrix, and it comes out like this. And I've included a little optional bit in here where you can say what it's equal to. So my KE is this 4x4. And you'll see that if I just did print KE, it would look like, oh, it's not defined. Doesn't look as pretty, basically. And even if I did what I'd done previously, which was SymPy pretty print, so sp.pprint sp.matrix, still doesn't look quite as nice. So this just enables me to include some LaTeX and some nice formatting. So this is going to be useful whilst we're going through this today, because it will help us explain things. So we're going to have a look at this problem. What we want to do is work out how I can take this 4x4 and expand it into a larger matrix. And what do I mean by expand it into a larger matrix? Well, my global stiffness matrix is going to be 2n by 2n, with n being the number of nodes. And then correspondingly, these nodes are going to refer to a different part of it. And let's just think about what that meant for the simple problem that we looked at. So we're going to solve the general case in here, and I'm going to occasionally refer back to the simple case just so we can think about things. So let's look at this problem here. I've already got this drawn up here, so I don't need to go through this. So my stiffness matrix for this element here, which we had element 1, let's call this K1, would be a 4x4. So 1, 1, 1, 1. Yeah, let's just call it ones at the moment. It's not ones, but I'm gonna just say it is for the purposes of being able to talk about where these elements go. So this is my stiffness matrix K1, and this relates the forces on node 1, sorry, the forces on element 1 at node A and node C, and the displacements at node A and C here. So this local problem would be K1 UA VA UC VC is equal to put a little subscript 1 here, because these forces on the right hand side would only be for this given node. Okay, I'm only, sorry, for this given element. So I'm only just drawing this to demonstrate what this matrix does. So we've got node A and node C. So I've sort of skipped a little step there because we previously had these written down as U1, V1, U2 and V2. For element 1, node 1 is node A. For element 1, node 2 is node C. Okay, so that's what this relates. So since this is a 4x4, I need to then expand this into a matrix that still gives me the same equations here, but what I want to have it such that it can be a 6 by 6, so that when I multiply it by the 6 by 1 global displacement vector, then I still have the same set of equations. So that's going to end up being 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. I've not drawn my bracket large enough. 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Okay, and then this will be multiplied by UA, VA, UB, VB, UC, VC. And in fact, the way that I wrote these forces here, that's not really a suitable way to write these. What I should have written, I should have really written lowercase fx1, fy1. Okay, so this is then the forces in the x and the y directions, which are the global directions on this element only. Okay, and then actually for these fx1 and fy1, those are equal to fxa and fya, but these won't be, because we've got to combine the sum of the forces here with the forces on element 2, and so fx2 for this node plus fx2 for element 2 as well. That would then equal the force on node C. I'm getting a little bit sort of tied up here with explaining this. What I really want to say is that we take this 4 by 4 and we've expanded it by putting it into this 6 by 6 and making sure that we've still just got the same relationship. We're looking at node A corresponding to forces on node A and displacements at node C corresponding to forces on node C. And then anything related to B is just zeros in between. So the way that we're going to make these matrices is by starting out with a 0 matrix that's equal to 2n by 2n, and then we're going to figure out how we put the rows and columns from this 4 by 4 into this big matrix here. So let's go over to Python again. I can get rid of this printing bit here. So let's just start a new hypothetical problem. We've got this 4 by 4 matrix here, and I've got just this unity matrix. This would really have some numbers in there, but it's just nice and easy to see what ones are. Okay, so we can use this for helping us out. So let's say that we've got a problem with 5 nodes. And we're going to call those A through E. So we give them Latin letters A through E. And so we need to take this 4 by 4 and then expand it into a 10 by 10. Because we've got 5 nodes, we've got 2 displacements associated with each of these, which gives us a 5 by 1 global displacement vector. So the first step that we're going to do, and what we're going to try to do today, is just take this 4 by 4 and expand it into a 5 by 5 based upon the rows of this table. Okay, so we're going to pretend that we've got a problem with 5 nodes, so it would have A, B, C, and then it would have a D and E below here, and then we're going to do some expansion of those matrices to produce things. So in fact, let's just write some out. Let's write some elements out for this problem. So say we have some elements and a connectivity table. So we're not going to put in their x and y coordinates. I'm just going to say that I've got nodes and elements in this table, and that will enable me to work out how to expand these matrices. A, B, C, D, and E. So this would be my node. Again, if this is in the connectivity table that we had from last week, I'd have an X and a Y column here, and then I'd have different elements. But let's just ignore the X and Y. So we'll say dot, dot, dot. Let's say element 1. Let's look at two different things. Let's look at element 1 and element 2. So we'll say element 1 goes from node A to B. And we're just going to put two arbitrary sets of numbers on here. I'm then going to say element 2 goes from, say, C to E. Okay, so we want to use this information to see what our matrices are going to look like. So if each of these elements would have an associated 4x4 like this, it would have numbers in it. Doesn't matter this is ones, because if we can work out how to split this matrix up into the correct 10 by 10, we can then do it with any matrix that's based with, you know, numbers that aren't just ones in it. So looking at this, I can see that my global displacement vector is going to be UA, VA, UB, VB, UC, BC, UD, VD, UE, and VE. Okay, and it's a column vector. So I can see that my 4x4 for this element needs to relate nodes A and B. So it's actually going to relate these first 4 rows and first 4 columns. So my matrix for element 1 is going to have this matrix in the upper left hand corner, and everything else is going to be zeros. This one here, well, it's going to have some things in UC and VC and some things in UE and VE. So that's going to be the first, sorry, 1, 2, 3, 4, the 5th and the 6th row, and the 7, 8, the 9th and the 10th row and column. So 5th, 6th row and column, 9th, 10th row and column. Those pairs give us the 16 entries that we're going to place these in for element 2. So we're going to look at some logic that helps us work out how to put those individual elements here into some expanded matrices. We'll do this one first because it's simple, and then if we've applied the logic correctly, we'll be able to insert this one in here. Okay, so let's say that my connectivity rows, I've already got these in a table, I've imported it, and I've gone through it. So let's say my rows are, I'm going to put 2 lists in. So it's going to be 1, 2, 0, 0, 0. And the second one is, what did I say it was? 0, 0, 1, 0, 2. So this is now just a list of lists. I've got my two, I should call it my columns really, shouldn't I? Because they are, okay, these are my columns from my connectivity table. So this one corresponds to element 1, this one corresponds to element 2. So let's say let's just first work on the first column. I'm not going to put this in a list, in an iteration yet. So let's say first column. Let's just call it column for now. Column equals column 0. So we're getting this first one out. It's just going to be called column from now. Okay, so we've got this first one out, and it's now called column. Now what we want to do is we want to firstly look at the number of elements in this, and then that will tell me what the, so if I look at the number of elements in this list, that's going to tell me the number of nodes. So there are 5 nodes, and that then tells me I need to make a 10 by 10 matrix. So let's say and then we're going to make the expanded matrix as an empty matrix. So I'm going to say k expanded is equal to mp.zeros, and it's going to be 2 times n by 2 times n. And we'll do print matrix, which is that function that I created. There we go. Produced a 0 matrix. It's 10 by 10. Again, I'm going to put in a little latex string. K expanded. Let's put $signs around it because it is latex. There we go. So I've got my expanded matrix now. And I need to work out how to put these things in here. From here, these 16 items go somewhere in here. Now we know for this first element, they just go in this upper left-hand column. So we're going to work out the logic of how we extract that information, and then we will go through it. Okay. So this vector that we've got here is a 5 by 1. And let's think about what that actually means. Let me get rid of the screen a second. So we'll say that our information that we've extracted from the connectivity table is for this it's now a 5 by 1, or we'll say it's an n by 1, where n is the number of nodes. And so for this first one, it is 1, 2, 0, 0, and 0. And so let's just remember that for this problem, we've got our original 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. This is my element stiffness matrix. I've said it's just a 1, 1, 1, 1. There could be some numbers in here. It doesn't really matter yet. But this corresponds to U1, V1, V2, V2, fx1, fy1, fx2, and fy2. So what this is telling me that my 1 for this element is actually an A, and my 2 for this element is actually a B. And we can just see this because I could just write A, B, C, D, E along here. Now here's where it gets a little bit confusing. So each node has 2 displacements. Each node has got a U and a V. So what I really want to do is I want to say, okay, if I see a 1, take the first and the second row and the first and the second column. Because wherever I've got this 1 in here, that then tells me, for example, both this first and the second row correspond to A. And then here, this 2 is telling me actually the third and the fourth row correspond to B. So it would be better if I could then replace this with 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, because that would then tell me where these items go in the global stiffness matrix. So let's see if we can just do a little bit of logic to help me take this list and turn it into something a little bit smarter. I think I did this with a list comprehension earlier, but I think I might just do this using a nested for loop because that's probably a little easier to understand. I'm going to provide a complete, actually I'm not going to tell you I'm going to do that. You should be coding along with this. So we now want to take this column, and where it's now a 5 by 1, I want to turn it into a 10 by 1. Where there's the 1, there should be a 1, 2. and where there's the 2, there should be a 3, 4. Okay, because where there's the 1, that corresponds to row 1 and row 2 and column 1 and column 2, and where there's the 2, that corresponds to row 3, row 4, column 3, column 4. Okay, so we now need to take this, let's just have a look, print column. Okay, let's make np, let's say, I'm going to call this the nodes is an np array. I'm going to make an empty np array. And then I'm going to go through that list called column, and I'm going to, if there's a 1, I'm going to put a 1 and then a 2 in there. And if there's a 2, I'm going to put a 3 and a 4. And if there's a 0, I'm going to put 2 zeros in there. Again, I did this with a list comprehension earlier, but it might be easier with a for loop here. For in fact, let's do this as a list because lists are easy to append. So rather than doing this as a NumPy array, I'm going to do it as a list because lists are easier to append than NumPy arrays. So if the value is equal to 1, then we're going to put the nodes.append a 1 and a 2. Otherwise, if the value is equal to 2, then we're going to do the same thing, but we're going to put a 3 and a 4 in there. And if it's not a 1 or a 2, it must be a 0, then we're going to put 2 zeros in. And then we're going to do print column print the nodes. There we go. Okay, so I've taken my column here and I've then expanded it. So this is the original column, and then I've just made it to 1, 2, 3, 4. And this tells me actually where I put the items from my 4x4 into the global matrix. So let's just change this now. Let's just change this to looking at the second one instead. So I'm now going to say column is equal to my column's item number 1. So it's actually this one here. So I should now expect this to be 0, 0, 0, 0, 1, 2, 0, 0, 3, 4. That's what I expect to come out of this if I've done my coding correctly. There we go, and I have. Okay, 0, 0, 0, 0, 1, 2, 0, 0, 3, 4. Okay, so we've now been able to expand this, and we can see here this is a 5 by 1, which is what we wanted. Let's just go back to keeping this as the first column for now. And there we go. Again, I did this with the list comprehension earlier. You can actually do this in like a single line, really, if you want to. But I've chosen to do it as a nested list here because so a nested set of ifs, because that sort of helps us. So we've now got this here. This at this stage doesn't quite help us yet, because what this tells me, it says that actually I want to take my items from my original 4x4 matrix. I want to put the first row and first column, second row and second column, third row and third column, fourth row and fourth column, and all permutations of those into the upper left-hand corner. So what I want to do is I want to be able to work out what does that actually correspond to in terms of a Python index, okay? Because I'm still using sort of human numbers here. Python index is starting at 0. So what we want to work out is we want to see if we can extract these as a list of indices. So let's call this something else. Let's call this, let's say the indices. So now I'm going to iterate on that thing I've made called the nodes, and if there's a 1 there, I need to work out where that occurs. If there's a 2 there, I need to work out where that occurs, a 3 and a 4, for example. So I'm going to say for I in range. Let's show you what this does. Let's just remind you guys how lists work. Sorry, how ranges work. I'm now just going to go through here and do 1, 2, 3, 4, because that's what this does. It means I'm iterating on I. What I want to do now is I want to append the index where 1, 2, 3, and 4 occur, and I need to make sure I've got them in the correct order. And the reason I've got to make sure I've got them in the correct order is because I might have a node that, say, goes from B to A rather than A to B. So let's change that in here. Let's say nope, let's not do that. I'm in the wrong window. Let me go here. I'm losing my stuff on screen here. It's difficult to see. Okay, so let's use the np where function. Okay, so let's see what this looks like. So if I now want to print a Boolean of where the nodes is equal to that, it doesn't help me because at the moment this is a list. So what I think I'm trying to do here is say I now want to work out where in this thing I've made, which is called the nodes, where it's equal to I. Can't do that on a list. So I need the nodes to be a NumPy array. Okay, now when I do this, and I run through here, let's just do a okay, so now what this is going to tell me, so I'm going to go through this thing here, and I'm going through and looking for 1, then 2, then 3, then 4. So here I'm saying, where does 1 occur? Well, it tells me that 1 occurs at this Boolean, which is in the very first item. 2 occurs at the next one, 3 occurs here, 4 occurs here. If I had made the nodes the other way around, so let's say I'd got the nodes was equal to 3, 4, 1, 2, 0, 0, 0, 0, then okay, it would have worked the other way around. I would have got 1, 2, 3, and 4, and that's why it's important to have this sort of searching for where they occur in the correct order, because you might have elements that go from the wrong node to the wrong node. So I'm just going to take that line out of there, and I've now got this working. So that tells me where those items occur. I now want to say, well, this obviously occurs at the 0th position. This is the 1th position, 2nd, 2nd position, and the 3rd position using Python indexing, which starts at 0. So now I want to say I need to get this out. So let's use np.where. Let's show you what that is. So print np.where just tells you where the true values are. So it tells me here array 0, array 1, array 2, and array 3. Now where's annoying because it's extracted here. It's given me a tuple because it's in those round brackets, and it's then giving me an array. I actually only want the value that's in the array, so I need to say, let's have like if I put 1, 0 here, it extracts the first bit from the tuple, which gives me this array, and I actually just want the value, so let's put another 0 here. There we go. So this one tells me where those indices occur within that thing that I've just created. And so I'm now going to say the indices dot append and let's get rid of these printing things. And I'm now just going to say print here we go. So this first one here is the column extracted from the table. The second one here, I've expanded it into including 2 deflections for each node. And this one here is just telling me, well, what rows and what columns does that refer to in the actual thing? So this is going to help me take, this tells me basically for my 4x4, these are the rows and columns to put that 4x4 in your global stiffness matrix. So let's think, can I use slice notation to help me out here? Now, when I first started to do this, I was still in sort of thinking how MATLAB works, and I thought, can I then use this here to put things into my matrix just by telling it, put it in those rows, put it in those columns. Let's have a look. So let's try K expanded, the indices. And K is my 1x1, yeah. Okay, doesn't like it because I put a space in there, but it's not going to like it anyway because, yeah, it doesn't like this anyway here, but this bit down here tells me shape mismatch, value array of 4x4 could not be broadcast to indexing result of shape 4. So the way slice notation works, if you provide 2 lists here, which is what I provided, then it says, okay, I'm now going to try and put 1 item into 0, 0, 1 item into 1, 1, 1 item into 2, 2, and 1 item into 4, 4. And that's not actually what we want. We want to put something in the 0th row at columns 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3, and so forth. So we need 16 values out of here, whereas the way that slice notation works, it will only put 4 values in. So this took me a bit of figuring out how to get to work the first time I did this. And we actually need to use a little inbuilt part of NumPy. So I can then provide this same set of the indices here. But I'm going to say, I'm going to put it in np.ix and use an underscore underneath it here. If I run this, it seems to have done something. Let's do a print matrix K expanded. Here we go. I've put my things in the upper left-hand column, sorry, upper left-hand corner of this matrix. So let's just have a look at what this np.ix does. Okay, produces the first one is a column vector, second one's a row vector. Okay, so that just takes those indexes that we've got and enables me to put them in properly. I probably could have, well, I could have done the same thing. I could have said put this as an array of the indices transposed and then the indices in here, but it's just easy to use np.ix here. So that works. Let's try changing this over to using the second column up here. So let's go here, change this to second column, which means I've now got 0, 0, 1, 0, 2. Let's run this line of code. Okay, so I've got my second column out 0, 0, 1, 0, 2. That corresponds to 0, 0, 0, 0, 1, 2, 0, 0, 3, 4. And that's telling me actually I now want row 4, row 5, row 8, and row 9, and the corresponding columns equal to those as well. So if I run this now, here we go. It's put items in row 5, row 6, row 9, and row 10, and then the corresponding columns equal to each of those as well. So we found the correct 16 parts to put in here. Okay, so that is how we're going to expand these matrices, and once we've got them in this format, we can just add them together. So we do this separately for each element and produce a new 2n by 2n matrix, add them together, and that is our global stiffness matrix sorted out for this problem. So I really want you guys to code this up and go through and try and understand it yourself and look at some of this problem. I am going to include a worked example of what I've done in this lecture today that's available on the Slack site as well. okay, because I'm sure some of you will make typos in your code, and I include a couple of further examples showing how this works with a bit of improved description within the text, so you can see what's going on here. Again, the starting notebook for this is available for download. It's available on the YouTube site, and I'm going to include an expanded, terrible pun, an expanded version of what I've just completed today for download on Slack. So at this point now, you should be happy with if you have a table that looks like, let's find it. If you have a table that looks like this, you should now be able to make 4x4 matrices for each of those elements. You could have as many elements as you want. You could make 4x4 matrices for each of those. And now you should also be able to take those 4x4 matrices and expand them into 2n by 2n, where n is just the number of rows in your table corresponding to the number of nodes. Okay? And now we've got them all, you've got to add those together. Add them together, you've got your global stiffness matrix. You know your global displacement vector because it's UA, VA, UB, UC, UB, VB, UC, and VC, and so on for the number of columns you've got. And then the forces would just be FXA, FYA, FXB, FYB, FXC, FYC. So we're going to do that. I expect you guys to be able to do that yourself, okay? Because the next lecture that we're going through, we're going to continue solving this problem. Okay, that's going to be going through this problem and producing the same matrix that we found by hand, doing it programmatically. So I expect you guys to have a good grip of what we've done today and a good grip of what we've done in the previous lecture, so you guys can understand how to do all these different parts. Okay, hope everyone's enjoying this so far, and I look forward to finding out all of your Python woes and all of the problems you've been having with the finite element method. But I hope this is really starting to make sense to you guys now. Once you've figured out, quite what this matrix means and why it's useful, you'll see how it's such an incredibly powerful tool to use for structural analysis. Okay? And understanding the basis of how this works is more important than understanding how to use CATIA, for example, because this shows you how these bits of software at a very basic level sort of actually work. Okay, so have a good weekend, guys, and I look forward to seeing you in the review in about an hour and 10 minutes. Take care.